Our next keynote is Dr. Debendra Das Sharma, who's an Intel Senior Fellow in the Data Platforms and Artificial Intelligence Group, and he's Chief Architect of the I/O Technology and Standards at Intel Corporation. He's a leading expert on I/O subsystems and interface architecture. Das Sharma is a member of the Board of Directors of the PCI Special Interest Group and a lead contributor to the PCI specification since its inception. He's been very active in all the standards organizations, including right now he's co-inventor and founding member of the CXL Consortium and co-leads the CXL Technical Task Force. He also co-invented the chiplet interconnect standard UCIe and is the chair of the UCIe Consortium. He has a bachelor in technology with honors degree computer science engineering from the Indian Institute of Technology and a PhD in computer engineering from University of Massachusetts Amherst. Same place Dr. J went to school. Don't think he knows Dr. J, but that's okay. He's a frequent speaker at not just our event, but so many conferences and a distinguished lecturer. And he's been awarded Distinguished Alumnus Award from his university and also Outstanding Engineering Award from the IEEE. Let me introduce to you Debendra Das Sharma.
Thank you, Jay. Greetings, everybody. It's nice to see people after such a long time. I'm going to talk about how Compute Express Link, or CXL, is changing the compute landscape. The agenda for today is we'll talk about load store interconnects in the compute landscape. Then we're going to talk about CXL and its evolution. Next, I'm going to go on a limb and talk about the future directions with CXL innovations, my thoughts around it. We all know that, as seen in the slide here, the IDC data, that we are seeing explosion of data. And that's leading to a lot of opportunities with the data-centric revolution that's ongoing. And with so much of data being produced, we need to move that data faster. We need to store more data. We need to process that data in a timely fashion to gain insights. And we need to be able to do this seamlessly, efficiently, and securely. And that's the challenge that a lot of the ecosystem is trying to solve. If we look into the cloud landscape today, what you see is a picture in the middle. You basically have racks of server. They are connected through a networking interface, and be it Ethernet, be it InfiniBand, or what have you. Short distances, copper; longer distances, optical. Within each rack, as you can see on the picture to the left of that, it's basically a set of drawers. And those drawers are chassis, if you want to call them. A compute drawer, storage drawer, memory drawer, those kind of things. And each of them is like an independent server node consisting of multiple CPU sockets, typically 2-socket systems connected through a proprietary cache-coherent interconnect. A lot of I/O devices such as GPUs, FPGAs, storage devices, SSDs, and you're going to connect to the network through a NIC card. So that's basically the connectivity today. And what you have is, going forward, we need to treat this data center as a computer. And interconnects are key to driving warehouse scale efficiency. If we look into the data center today, the resources that are assigned to a given node, whether it's memory, whether it is GPUs or accelerators or what have you, those are all captive resources for that particular node. If I'm running a task in a given server today and I need, let's say, for that task, an extra terabyte of memory, there is no way for me to go and borrow that memory in a coherent manner from a nearby node. So same thing with the accelerators. If I have a need for that, there is no way for me to really go out of my node. So those are all captive resources. Those are the types of problems that we need to solve in order to address the challenges of this data-centric world, right? So here's my taxonomy of the interconnects. I break up things into two categories. So there are the networking type of interconnect, so which are or the fabric, which are at a data center scale. These tend to be latency tolerant because of the scale in which they are deployed. Typically, they are at the bleeding edge of data rate, right? 56, 112 gig going to 224 gig. The faster you can drive, the better off you are. Narrow links, again, because of the scale in which they're deployed, 4 to 8 lanes. And as I said, latency is not the primary concern. The second class of interconnect, which is the load store interconnect, these are the ones, as the name indicates, load and store, which are basically memory read and memory write semantics. So they have got architectural ordering semantics built into them. And these are examples of this are PCI Express. What I'm going to talk about is Compute Express Link, CPU to CPU cache coherent interconnect, like such as Intel's UltraPath interconnect or UPI. These are extremely latency sensitive, where even nanosecond worth of latency can have visible impact on the performance that you deliver. Typically, you will see hundreds of lanes. So for example, every CPU socket has got hundreds of lanes of PCI Express today. You got another hundreds of lanes in which you are connecting to your neighboring CPU. So these are in hundreds of lanes on the motherboard, and we'll talk about how it is gradually moving towards the cables and the backplane, especially in the context of Compute Express Link. So the picture in the middle there shows the node level connectivity. That's where the load store interconnects are, and gradually they're moving to the rack and beyond, and we will talk about that. There is another class of interconnect of the load store category, and that's a newly introduced interconnect that we announced in March of this year, Universal Chiplet Interconnect Express. These are the die-to-die interconnects meant to effectively bring the same type of plug-and-play infrastructure that we have at the board level with PCI Express and CXL onto the package level with chiplets. And fundamentally, we have mapped PCI Express and CXL as the protocol of choice. These are uber latency sensitive. You have the frequency 4 to 32 gig. Thousands of lanes is the scale at which we are looking at. So naturally, the power challenges are huge there. It's ultra low power. So just to give an idea, 0.25 to 0.5 picojoule per bit, that's the amount of power that we consume there. And that's an order of magnitude lower than external interconnects. These are also ultra low latency, again an order of magnitude less than external interconnect like PCI Express CXL, and very high bandwidth density. 2 to 3 orders of magnitude more bandwidth per square millimeter or per millimeter of the die edge kind of area. So we introduced this one in March of 2019. Intel donated the initial UCIe 1.0 specification. Several of us have been working on it for more than a decade, like we have been working on CXL before we introduced in 2019 of March. So, and I'll talk about the connection between UCIe and CXL towards the end of my talk. Just keep that in mind. So load store I/O basically goes from a package level all the way to, of course, the node level and to the rack level and beyond. Now, some breaking news. We incorporated, UCIe incorporated in June of this year. We had elections. We added 2 new board members. So with the original set of 10, we have 12 new board members, 60 plus members. UCIe is poised to really change the compute landscape, similar way that CXL is well on its way to in terms of changing that. Now let's talk about Compute Express Link and its evolution. The picture on the left shows the world with only PCI Express as it existed prior to 2019. Right? So we recall that in 2019 March, CXL consortium got initiated. Intel donated the 1.0 specification. I'll talk about subsequent specifications that happened in the consortium. And with that, with PCI Express, it's a load store interconnect, which means that memory reads and writes are what goes on across the link. But memory that is attached to the processor, those are all cacheable memory. But who gets to cache them? Only the CPUs gets to cache them. all accesses through the PCI Express link are non-coherent accesses. Similarly, memory that is attached to the PCI devices are uncacheable memory. So the fundamental ordering paradigm there is the producer-consumer ordering paradigm, and that really works well. It has worked beautifully for the last 3 decades, and we want to preserve that. But as we see newer and newer types of applications arise, we see the need to also have the model on the right in addition to the model on the left. And what that means is that you want to have your accelerators, as we do more heterogeneous processing, you want your accelerators to be able to cache the data and also do finer grained data sharing with the processor as well as with other accelerators instead of having to do bulk data move as you do with PCI Express. So caching semantics enables that, and by the same token, memory that is attached to the device needs to be able to be mapped to the coherent memory space. That's what basically CXL brings to the table, and we'll see how it does that. Some of the other problem statement is around the system memory challenge. The picture on the left shows how the number of core count has increased. This is courtesy Meta. But the memory bandwidth per core is going down. And that is true even as we are adding more and more memory channels. Fundamentally, DDR channels are just not able to keep up with the bandwidth demand that the compute infrastructure demands today. Picture on the right shows the price per gigabyte bit of DRAM, and again, courtesy Meta, right? It's flat. So as we are getting to this more and more compute capability, we need more memory to feed that beast. And guess what? The cost of memory is going to rise exponentially along with that. What about the demand side? Well, demands for this machine learning application, demand shows no signs of abating. It's on a cliff, right? And fine, we can meet that demand through heterogeneous processing, different types of acceleration function, but we also at the same time need to solve the memory problem. And that's basically what CXL does. So the approach of Compute Express Link is to build a coherent interface on top of PCI Express. We do not want to reinvent the wheel, right? That was the approach we took back in 2019. It leverages PCI with 3 protocols. So you got CXL.io, which basically is responsible, which is similar to PCI Express, which is responsible for doing device discovery, configuration, interrupts, address translation services, and of course the direct memory access kind of bulk data move. So that's preserved intact. On top of that, PCI Express 5, and that's mandatory. .io is mandatory. On top of that, we got 2 optional protocols. One of them is CXL.cache. Basically, it has got caching semantics. It enables a device to cache the data that is mapped to the system coherent space. And you also have .memory semantics, which enables the device to map all or some of its memory into the system coherent space. The other attribute is low latency. How low is the latency? We want the latency across the CXL link to be similar to that of a single hop away in terms of the NUMA latency on our UPI link. So, load to use access latency is expected to be significantly less than 200 nanoseconds, right? Similar to what you would see in a 2-socket system, right? The third aspect of it is asymmetric complexity, and this is an important aspect. You notice that there is something called home agent on the host processor side. This is the one that is responsible for orchestrating cache coherency between different caching agents, resolving conflicts, all of that. Home agent functionality changes with every microarchitecture generation. It's vastly different between different computing architectures. So for CXL, we took the conscious decision that you can bring your home agent along. What we really need on the device side is a simple set of messy cache coherency protocol, right? Things like, hey, I want to cache this line shared, private, exclusive, right? All of those things using messy terminology. And I can do the write back. Occasionally, I might get a snoop, and I give a snoop response, right? Those are very simple set of protocol enhancements that we built. And by the same token, if I'm doing memory, I really don't need to understand anything about how cache coherency gets enforced across the system. All I need to do is, you send me memory reads, memory writes, and I'm going to do that. You might have some metadata, which will be your directory. Fine, I don't really need to even know what those directory bits mean, right? So that's the simplicity that we bring with CXL. So 1.0, 1.1, the first generation of CXL, there are 3 types of usage model. It is direct connect. And the type 1 devices are those that have CXL.io and CXL.caching semantics. And usage model would be, for example, if you are doing a smart NIC and you want to do PGAS, which is partitioned global address space. If you want to have that semantics, PGAS ordering semantics are very different than PCI Express ordering semantics. So if you didn't have CXL, and you're doing that over PCI Express, you would basically serialize it in order to enforce the PGAS ordering semantics. But with CXL, you can go ahead and prefetch all of those lines into the cache and complete them in your local cache in the program order. You can also implement smart atomics. You don't really need to do anything. You just you get the cache line into your cache and do whatever advanced form of atomics you want to do. So that's possible. Type 2 device, the second category. All 3 protocols are involved. You can, of course, work with the CPU and other accelerator in a fine-grained manner because you are doing CXL.cache. And you can also map your memory into the system coherency space. So you can write data to your local memory. It is mapped, and others are going to be able to see it. And you don't need to do this bulk data move back and forth, right? So this enables those kind of usage models. Last, but definitely not the least, is the type 3 devices. So these are the memory buffers. And you see a lot of people making their product announcement, which is extremely pleasing to see, right, for somebody who has worked on the technology for a long time. And these are done for the purposes of things like memory bandwidth expansion and memory capacity expansion, right? Because now you can just add a memory buffer. And by the way, CXL is memory technology agnostic. So you can put your memory controller is on the device side. And you can put any kind of memory there, and you can even do 2LM, for example, multi-level tiered memory. And again, the protocols are .io and .mem. So that was the first generation of CXL. With the second generation of CXL, what we did was we brought in a few other things. We introduced the notion of what is known as pooling and switching functionality. What pooling does is, if you look at the picture on the left, you got a bunch of servers, you connect to a CXL switch, and you got a pool of memory. In this picture, it's a pool of memory. You can imagine it's a pool of accelerators also. I'm running a task on a given server, and going back to the example, now that task needs an additional terabyte of memory. Well, what do? Well, I just go across the switch, ask for that terabyte from the pooled memory. If it is available, of course, I'm going to get that. And now it's part of my system memory space as if I had the DRAM next to me. And yes, you got an extra hop of latency, but that's like a NUMA hop. We all know how to deal with that. Same thing with the accelerators. You can go across the CXL switch and ask for accelerators as many as you need, right? And then once you're done with that, you can release it. And we use the managed hot plug flows to do this resource allocation and deallocation. We also defined persistence flows in CXL 2.0. It's architected. And fabric manager functionality, software APIs to make all of these things happen. We did a bunch of security enhancements. Fundamentally, CXL 2.0 is a game changer. It enabled us to go from node level to beyond node level. This is the first time load store interconnects went from beyond node to across nodes. We solved that real hard problem using the CXL consortium and the combined effort of 200 plus member companies. Now coming to the breaking news, we recently announced Compute Express Link 3.0 specification. So what's there in CXL 3.0? Well, we doubled the bandwidth, 64 gigatransfers per second with 0 latency adder, unprecedented. In other words, latency in CXL 2.0 should be the same as latency in CXL 3.0. But more than that, we enabled fabric functionality. It consists of different components. I/O accesses, that's in CXL.io, we are moving those to be unordered I/O. Yes, the producer-consumer semantics will be held intact, but the enforcement of that ordering is with the source. And we are pursuing an ECN through PCI SIG to get to that point. You'll find that in the CXL 3.0 specification. We are also introducing the notion of accesses that goes to a type 2 or type 3 memory, HDM memory, to bypass the host if needed. And if there is a conflict in terms of coherency, then the device sends what is known as a back invalidate on the CXL.mem channel. It's a very simple construct, but it has got very powerful implications. Now, with this, what it means is we are no longer bound by everything going to the host to resolve coherency actions. A lot of those can be locally resolved. But most importantly, we are no longer bound by a hierarchical tree topology. You can do true fabric kind of topology, such as the one that is shown on the picture here. Some of the other things that we have done is introduce the notion of shared memory. Beyond pooled memory, we have introduced the notion of shared memory. What it means is that you got coherent memory that is shared across multiple independent servers. Hardware enforced cache coherency, so that you can use that for shared data structures. You can use that to do message passing. You can use that for any kind of purposes that you want. So fairly revolutionary set of constructs that we have used to do CXL 3.0. So now, where do we go from here, right? This is where I have to give my opinion of where things can be moving forward. Well, the simple one. Today, we can construct a common platform with CXL memory. So you can have some number of DIMMs. If you look into a lot of the, whether it is OEMs or cloud service providers, different platforms have different number of DIMM channels because you have got different number of cores or different compute requirements. Now you can do a common platform, and if somebody needs more memory capacity or memory bandwidth, you just use the CXL links to provide that. And guess what? It's a NUMA hop away. So that's well understood, right? You also get scalable bandwidth, both in terms of width and the frequency. It's very low latency. There is nothing that beats the pin efficiency of PCI CXL type of SerDes links, right? 64 gigabit per second means that you get 32 gigabit for every pin, if you take the differential into account, right? And the bandwidth numbers are shown there. And the other thing that's happening is memory is now serviceable with a front-loaded form factor. You can do that. Going forward, over time, I can envision less and less traditional DIMM slots and pretty much memory moving to CXL. Next set, persistent memory innovations with CXL. It makes sense to me that NVDIMM just moves over to CXL. This is DRAM that is backed by storage class memory in NAND. And the pros are that it is going to be serviceable. It's going to be highly available. You can make it dual-headed if you want. You are no longer constrained by the 15 to 18 watt power profile that exists for a DIMM slot. And you do not have to take up a precious DIMM slot. Those are the huge benefits that are offered by Compute Express Link. Persistent memory is now going to be cacheable. So imagine that, right? You can have multi-headed for failover. You can do serviceable hot plug. And with persistent memory, what you can do is that you can put like a memory tiering there. You can have front-load it with a DRAM as a memory side cache and have the rest of them be mapped into the coherent memory space. And of course, you are going to use things like the HMAT table to notify to the user that, hey, this memory is different than your flat DRAM memory, because if you miss on the DRAM cache, you are going to have extra latency. So and there are lots of applications that can take advantage of that. And especially they can do things around cold tiering, hot tiering, warm tiering, right? And just take advantage of that in that particular way. Next, we'll talk about computational storage through CXL. Today, you can put an accelerator in front of your storage and do computational storage, even with CXL 1.0 and 2.0. Going forward, you can just have a CXL.mem type 3 device and do computational storage, where you can basically are doing acceleration, things like compression, encryption, RAIDing, right, search, all of those kind of functionality you can do on the device side. And the back invalidate thing that I mentioned a few minutes back can be used for the device to basically ensure that it has got the latest and greatest data. What is more is that these devices can connect to each other through a backend fabric and still be coherent with respect to the rest of the system memory. Because remember that we said we are bringing the notion of fabric. We are no longer bound by the tree hierarchical topology. And we can still get to leverage the PCI Express services like your NVMe, your device driver, your management infrastructure, all of that. Fundamentally, CXL enables us to scale with heterogeneous processing and memory using shared cacheable memory space that is accessible using the same mechanisms across all the devices. Some of the more future-looking things, as we saw, CXL is enabling new usages beyond the node. This is the first time that we get to realize, and this has got serious implications in a good way, we can build composable systems at the rack and the pod level. If you look at the picture on the right, that shows my view of the world. You got a bunch of compute nodes, right? It can have some amount of memory. You got a pool of memory, and that doesn't need to be the same type of memory. It can be heterogeneous memory in there. You got a pool of accelerators, different types of accelerators. You got a storage pool there. You got an infrastructure processing unit connecting to the networking world. All of them are connected through load store, coherent, compute express link that comprehends multiple independent domains, and you can use that to build a domain with more memory, more acceleration, and you can change that over time, right? That's the composability. So we have shared memory. We talked about that. We can do message passing. We can do more advanced atomics. Peer-to-peer is another thing that we can do without everything going through the host. Fabric manager capability. And what's important is for us to be able to build very low latency switches. It's my personal belief that you can do switches that have got 100 nanosecond latency round trip, right? Of course, existing switches have more than that, but people are going to come up with better designs. We can use cables with retimers to reach within a rack. And I'm going to talk about, with co-packaged optics, how we can reach beyond the rack. And the challenges are that, once you have build this larger system, your blast radius tends to be larger, right? So you need to think about that, how to handle those, containment, quality of service, right? All of those things, right? We need to solve those problems. It's a journey, right? The journey has not ended. Clearly, we are going to keep on innovating. This picture here shows the connection with UCIe. You can have a pod of racks. If you look at the picture on the right side, the top right, CXL switch package, you can see that you can construct a CXL switch using different chiplets. Some of them are noted as UCI retimers, so those are basically optical to UCIe conversion entities connected to switches, which can be, again, by themselves be scale-up kind of things using UCIe. And then at the bottom of that, you're connecting to a pool of memory or to a pool of accelerators. Similarly, from the CPU package, the picture at the bottom, you can use CXL protocol, but use UCI retimer and basically escape that package using co-packaged optics. Now what happens is that I can connect to any such CXL switch package within my rack, or I can connect to somewhere else. And now I get pretty large-scale systems with 2 levels of switching. You can basically construct an entire pod. You can reach an entire pod, right? Because those are the numbers increases exponentially there, the connectivity. So it offers us real connectivity options there. So with that, thank you all very much.